So the first part right here, a random sample, and I'd like to outline, this is very important, a random sample right there to start. From Stat Tool 1, the semester contains 65 students who got a C or better. Now I'm posting some new videos on a little thing called YouTube where I highlight what we're talking about here. When you get questions like this, don't even look to what it's asking you yet. Start noting what you need to know. 109 is N. It is the sample size. Now, a lot of people, I know someone here might know, what is 65 students got a C? I heard sample proportion, which is kind of good. It'll help you find the sample proportion in notation, and a lot of people forget this. 65 is actually X. It will help us find the sample proportion via the formula P hat equals X over N. P hat equals X over N. It is the number of successes in the sample, so as long as you know, that is going to help us find it. Now, in my class, we talk about Mr. T. I'm sure Mr. T is a really nice guy, but I also say Mr. T is mean. On this test, it's important to know that the T distribution is used only for mean. What question did we ask people to plug in this data? We had one. Someone said, in Stat Tool 1, did you exactly get a C or better? Now, when someone answers that, they're answering yes or no. You could do a quantitative to this. You say, what was your grade? I'm merely asking you, did you get a C or better? So when we look at this question here, we can identify that this is a categorical, which means we're dealing with proportions. I make notes on this on my test so I know what kind of formulas I might be using. We're dealing with proportions here. Questions were yes, no. So that helps us down here when we see a 95% confidence interval, we know we're not dealing with T, which automatically puts it to one answer. Now you might say, why is it not 1.96? That goes back to our old 68, 95, 99.7 rule. Within plus or minus 2 standard deviations, we have 95% of the data. So when you go down to minus 2 and positive 2, 95% of the data is contained in plus or minus 2 standard deviations. But we lied to you because it's actually 1.96. So let's go down here. Use the critical value circled above to construct the 95% confidence interval. And this is where, if you have already filled out some of the tests, it will help you out if you have the notation down. I immediately suggest going back to your sheet back here. And you'll notice some have proportions, some have means. Very, 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 very important right there. And we really only have these choices right here. Also seeing the Z, you'll see everything in here. We have P hat, Q hat, all this good stuff right here has been constructed for us in the formula, and we filled out everything because P hat equals X over N, and Q hat equals 1 minus P hat. Everything else is solved for us right there. Q hat is just the complement. If P hat is 0.8, Q hat is 0.2. Q hat 0.8, P hat 0.2, or vice versa. P hat 0.8, Q hat 0.2. They add up to 1. That's how to find them. So let's go back to the past and take a look at what we got here. Use the critical value. Now, every confidence interval has in it 3 parts. You'll notice this other times we do this on the test today. We have here the center of our confidence interval, which is going to be 65 over 109. And who can tell me here what P hat equals? Say that it's 63. Could you open it? They really wanted this review. And put the binder there. I think that's because I got the answer wrong. 0.6. Oh, 0.596. 0.596. Hi. Is there a bunch of people? Did you guys put the notebook in the door to keep it open?
Yeah, we got it.
All right, thanks.
Hey, Ryan.
Hey! Who's that? Let's go right here. You're quite strong. All right, let's see here. We need P hat times Q hat over N. So P hat is 0.596. Q hat, don't tell me, is 0.394, correct? Better be careful, I'm in pen. Oh, I'm way off these days, guys. It's 406. I was in Virginia yesterday. I think that might account for this. 404 error right there. I don't even know what I was thinking. If you notice, very specifically, I want to point out right here, I can't do algebra, but I can do statistics, or arithmetic rather. These two numbers add up to 1. Now on the bottom, P hat times Q hat over N, and N is 109. That's not going to help my head. Right there, P hat times Q hat over N. I'm going to pull up my handy-dandy calculator right here. I wish we had the screen. P hat, I tell you what, does anyone have a TI calculator I can borrow or just a regular calculator? So sorry to be the teacher I can borrow. Oh. Okay, let's do this. Got the best TI calculator right here. We're good to go. So let's do P hat times Q hat over N and then square root. I would do it in this order right here to solve the inside first. P hat times Q hat over N square root. That solves the inner portion right here. And now we need to times it by 1.96. You can stop right here because you found out something very important. You have found out the margin of error. If you are talking to the read, make sure you're talking in a whisper, whatever you do. Make sure you're in a whisper. So here we are. This is our interval right here, but we can go ahead and actually describe the interval a little bit better. Let's go ahead and enter in 0.596, and let's add to it our answer. And this is the upper portion of our interval. And we don't care if you do it with decimals or percentages. Either or is fine. And let's see if you have in it what I can do with mine. Nope. Sometimes you can press up. Go. 50.38%, and it rounds up, so let's do a 9 right there. Sorry about the messy handwriting. This is our interval right here. Now I want to point to something very important. You can double check all these. Does anyone know how to do these on the calculator really quickly? Anyone? This is something you'll have to practice. It's not that hard to do. You can go to stat, test, 1 prop z interval. Stat, test, 1 prop z interval. Enter in here 65, 109, 95% confidence, and we get our interval right there down to even better decimals. That's everything carried out for us with all the decimals exact. Stat, test, 1 prop z in, solves it immediately. Stat, test, 1 prop z in, and it solves it. When you get here, you type in X, N, and C level. So you have the notation stat, test, 1 prop z in. I don't care if you show work in my class, but I highly suggest being able to do it both ways. You could just write this technically in my class. I'm all right with that. One thing I want to note, I have videos on how to do everything on the TI calculator on my channel, and the videos are less than 2 minutes. They're very, very short videos. If you're confused, I'll email you the list. I'll give you email cards at the end here. But it's very easy to do very quick, and it's a good double check. Make sure you get those 3 points. The 3 conditions, you'll notice here are 6 points. This should be 6 easy points, or at least 4 easy points. Condition 1, random. That means they're randomly selected. The problem states it. Random, and the problem says it. I would write the problem states are randomly selected. Condition 2, 10%. We need to select less than 10% of the population. So we have to assume there are more than 1,090 Statistical 1 students. Does everyone see here that 1,090 would be 10%? So you could say, assuming there's more than 1,090 Statistical 1 students, we meet the 10% condition because we would not have sampled more than. I simply just times the original by 10 to figure out what it needs to be the population size, at least the size of. So we're probably good there, 10% condition. You cannot sample more than 10% of the population. Last but not least, this goes back to figuring out what the problem was. This is categorical data right here. So very importantly, when it's categorical data, it's the what condition? Success, failure condition. And the problem does state, suppose there's a 1,180, so we're good there. So the success, failure condition, you might want to write out in a little bigger terms than that. Valid confidence interval, now the NP hat is greater than 10, and NQ hat is greater than 10. And the really good thing about this is NP hat is actually X. And I can show this to you because X is 65. So let's take P hat here of 0.596 and times it by 109, and we get 65, just a few decimals off. So X in your confidence interval is the number we have for the sample. Does that make sense? It's like the number in the sample. When you let NP hat, it can almost be read the number of successes in the sample, the number of failures in the sample. So pretty easily we could figure out right here, might not be perfect mathematically, that is equal to 65, and then we could take 109 minus 65, and that's 44. So there were 44 failures in the sample and 65 successes, so we are good. Now a lot of people might ask, greater than or equal to 10, what if it's exactly 10? And the answer is I hope we never write a test problem like that, because 10 is just an arbitrary number. 10 is just an arbitrary number. How are we doing, guys? Last semester, 48% of Stat 1 students got a C or better on exam 2. Write out the appropriate null hypothesis to test whether the percent of students this semester who got a C or better on exam 2 is different. Keyword right here is different. Now, whenever you write a null and alternative question in the back, go ahead. Say it loud. What is it? Go back to the previous page. What was it? If it is quantitative, the third condition will be nearly normal. If we have means, the third condition will be nearly normal. If it's categorical data, one variable categorical data, it'll be success failure. So success failure is only on this test for one proportion data, like the amount of seniors in a class. Do we have evidence that more than 25 seniors in the class? Build a confidence interval for the true proportion of seniors. You have to ask someone, are you a senior or are you not a senior? That's categorical data. That'll be success failure. If you see quantitative anywhere, it's the nearly normal condition for the third. They always give them in order, but technically these have no order. You could say success failure, random 10%. There's no order. I just like to do it in order. Because 1 and 2 are always the same. Question? Sure. No, you will not have to memorize any Z-scores. That's a really good question. You will not have to memorize any Z's or any T's. We will give you the Z's or T's on the test. I have them memorized. It can help a little bit, but you do not have to memorize any Z's or T's. Good question. Good luck. Sure. You could solve these out by putting in N is 109, and then P hat is 0.596, and then Q hat is 0.404. So you could solve this is X over N, and this. But if you look at this, I want to show you something real quick right here. N times X over N, because what is P hat equal to? P hat is equal to X over N, right? So if you put this in here, what do you get? So that's why the math works out like that. P hat is x over n. So if you substitute that back in, you get x just by virtue of multiplying it by n. So just a little bit of math right there. If you don't want to remember that, just remember n p hat and q hat. And remember, that is for confidence intervals, because our confidence interval, we only know p hat and q hat. Okay. Now this right here is one of the hardest parts for people. Writing out the null and alternative is not that bad if you know the format of it. And I keep saying the videos. Sorry, I keep pimping out my own videos, but I'm putting up more videos that go over how to write nulls and alternative steps on the way. And did you see the new video? There's a new video I have that goes you through the whole step of hypothesis testing. And I'm going to have one for each chapter. It's just, they take time. So let's write a null and alternative here. To start, we need to say the null hypothesis states. Very important right here. The null hypothesis states. And if we are doing categorical data, we are going to talk about the true proportion. There's only a few things that can go in there. For you guys, you will have P, mu, mu1 minus mu2, or you will use the words independent. And then if you are doing an alternative, you will still have the same, but here at the end, it will be not. We'll talk about that later on. These are the only options for the parameter you're doing. Do not put anything else in right after the null states other than P, mu, mu1 minus mu2, or that two things are independent of each other. So if you think about what chapters you have right here, this chapter is chapter 17, or 18 technically. Chapter 18, and we're talking about testing a proportion. It is a proportion, so proportion is P. In chapter 19, we're doing a mean. So if we test a mean, we're going to do what? Mu. In chapter 20, we're looking at the what with means. The difference between two means. And then in chapter 22, we want to see if two categorical variables are independent of each other, like studying for the test and passing the test, which would be, did you study for the test, yes, no? Did you pass the test, yes, no? So it's two categorical variables. In order of the way alternative hypotheses go, you have chapter 18, 19, 20, and 22 up there for you right now. Those are all your null hypotheses, or at least the parameters that will go in it. And the last one is the null. Right here, the null hypothesis states, and the null always has the equal sign. So you got some easy stuff right there. You could write a start of any null that we use statistical wording by putting the null states in equals, but now we have to start out with it being equal to something that we're going to test for. Here, we are testing to see if it is 48%. So the null states the true proportion of students who would get an A, or a C or better, excuse me, is equal to 48%, where the alternative states that the true proportion of students who would get this is different, and that is very, very key. That's why I underline it, and that's why we write different in here. So the null states that the true proportion of students who get a C or better is different than 48%. Let's go right here. Using your results obtained in part 2. What is your conclusion regarding your hypothesis test in part 4? Briefly explain, hey guys, make sure to not only whisper. Briefly explain how you came to this conclusion. Note, if you have no answer from part 2, use this interval as your answer in part 2 and then answer in part 5 using that result. So what we want to do right here is look to our interval. You notice the interval we give shares a similarity to the interval we have. I just want to double check because we're trying to see the students who got a C or better. In the interval we created, yep, it was for students who got a C or better, but our interval goes from 50 to 68. Does everyone see that? Our interval does or does not contain 48. Does not contain 48. The interval here does or does not contain 48. I'll give you guys a hint. When we give problems like this on the test, where we give you an answer like use this answer, we're doing it so people who got stuck on one part don't miss the answer on the next, and usually the answer coincides. So this is kind of a good check right here. If you are, checking your answer, you're like, I can't promise, but at least from what I've seen, it's out of this interval, be out of your interval. So if you see something wacky in your interval where you had it, it doesn't mean you're wrong, but it means history is not repeating itself in the way we give tests. That's just a tip right there. Okay, using your results, what is your conclusion? Do we reject 48% or do we fail to reject? Reject, and this goes back to your project. We reject the null hypothesis, and this is important right here. We need to state it in context of the problem. I would state I reject that the true proportion of students who got a C or better is equal to 48%. I have evidence that the true proportion of students who got a C or better is different than 48%. Does everyone see what I did right here? All I said was reject, have evidence. Anytime you need to state in context of the problem, you have to just reread your null and alternative. I reject the null, just read along with me, I reject the null that the true proportion of students who got a C or better is equal to 48%. I have evidence for the alternative that the true proportion of students who got a C or better is different than 48%. All I'm doing is reading the null alternative. So just I reject, I have evidence, and then read it as a sentence. So if you get down the writing of that, you can say your conclusions in context of the problem really easily. Now, if we failed to reject, it would simply be I failed to reject the null that the true proportion is equal to true proportion of students who made a C or better is equal to 48%. I do not have evidence that the true proportion of students who made a C or better is different than 48%. So, good income. So here we are. Now this goes back to your project again. The significance level for a test is simply 1 minus confidence level equals alpha. So this is a complement thing again. You could also know that confidence level plus alpha equals 1. I mean, they're complements of each other. So since we're using a 95% confidence level, our alpha level is 0.05. And this is specific to two-tailed tests. Because when you look at what a confidence interval looks like, a confidence interval we have a confidence interval on the left side and we have a two-tailed test on the right side, where the difference between the confidence interval and the test is basically the inside and the out. So you can see where if one has 95%, the other, by virtue, has the remaining 5%. So we have nearly identical stuff going on here. They will have the same result. If it's not in our 95% confidence interval, we will reject at the 0.05 alpha level on a two-tailed test. If it's inside of our 95% confidence interval, that means it's believable. Like I'm saying, oh, the true proportion is somewhere between 40 and 50%. So would I reject 48? No, because 48's in there. It could be between 40 and 50, so I fail to reject because it's in my interval. If I were to test it, I would also fail to reject it at the 0.05 level. 95% confidence, same result at 0.05 alpha. 90% confidence, same result at 0.10 alpha. Whatever the interval is, just take that and add up to 1, and you have the two-tailed test right there. Good stuff. Let's get the last question done here and see if there's more questions. If we increased our confidence level to 99, what effect will this have on the margin of error? You guys got it. Nice job. Because our interval was p hat plus or minus z star. The z star right here is found by going, try and draw the same one. If you think about your 68, 95, 99.7, I know this problem does not say 99.7, but this z star in here, which was basically 2, is now going to be closer to 3 because it's 99. And as you can see, 68, 95, 99.7, you're just more confident now. You're covering more of the curve. So when you go to a more confident interval, by virtue of confidence level, it is wider. Because, you know, my sister might come between, she just picked me up yesterday morning. Literally, I was in Virginia all yesterday at a family get-together. It was loads of fun. So if I said I am 90% confident my sister will be here between 8 to 9, I would be wrong. I should have said I'm 99% confident she'll be here between 7 and 10, and I would have been maybe right. She told me she'd be there at like 8:30 yesterday morning. Nope. We still got there on time. But as you notice, when I was more confident, I made my interval wider, right? Because I'm more confident the truth is going to happen there. I think that does it for this question. Any questions about one proportion z-tests? It'd be wider. I reckon it'd be wider. Okay. Oh, sorry. I already did one person in the face. I'm sorry. I saw your fear. You're welcome. No, this game is no, don't do it. Okay, let's start the next question up. Remember, in between, feel free to ask any questions, probably best time. So definitely keep it to a minimum talking between, and if you have to talk, whisper to the person next to you. Much appreciated. Just keep it to a whisper, and then get your jollies out between questions. Immediately, when I see this question, I see a contingency table. I know what chapter we're in immediately for you. Anyone know what chapter we're in? 22. Comparing counts. Because when we see a contingency table, we have what kind of variables? What kind of variables? How many categorical? Two categorical variables. Categorical. So we have categorical data. And if you notice here, you can look at the problem itself. I so rarely read these problems because it's us just trying to scheming a problem up. You get what I'm saying? But we just come up with whatever. We're looking at, is there any relationship between area of study that people transfer into and their initial major? Which you would think if someone starts out studying psychology, what's the probability they'll end up in statistics? Me. So who knows? So a task force, yada, 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 students, they're looking at this stuff. That really is all nonsense, except for the last sentence of, is there a relationship between initial major and the area of study they transfer to? This last sentence is of, is there a relationship, lets you maybe know that this is chapter 22. Because the null and alternative could be written that there is no relationship between the variables, there is a relationship. I like the wording that they're independent because it's the chi-square test of independence. So that variable x and y are independent of each other, and then the alternative being variable x and y are not independent. Complement of independent is not independent. So let's take a look. We've got the jump output, and this is where people get stumped. Now I want to point out some neat relationships here. The expected, which we should note, is the second cell right here. The expected is the second cell, and that might not be that way on the test. Always make sure whatever you're looking at, it matches up. So everyone see for this cell right here, it is an expected because it is a second one. So to get the expected, it is row total times column total over grand total. And I highly suggest solving it on your test like that. If you notice, I have row total, column total, grand total. And that is the equation written on your test right there. So we take 127 times 260 and then divide by 525. 62.895. Did I mess it up? So 127 is the column total here. Does everyone see that? And then the row total here is 260. Does everyone, I'm going to write more on this. The reason I'm circling these numbers is because they match in on this cell. Does everyone see if I line up those, that they match in on it? They're the respective ones right there. Row total, column total, grand total. I got 62.89 right there. Yes, I'll write right here. 260 times 127 over 525. That is row total times column total over grand total. Row total times column total over grand total. That is how to get an expected. Now, what is an expected? It's just if they are independent, we just multiply the probabilities. The probability of someone being a liberal arts and the probability of someone then being biology is this. Just the two probabilities multiplied together. Next, we need to get a chi-squared. The formula for chi-squared is observed minus expected. Note you need expected quantity squared equals cell chi-squared. So now we have a chi-squared right here. You can kind of figure this out. All we're looking at here is the difference between these two numbers. So I'm going to take and subtract those two differences. 13 minus, and I will say this, it does not matter which one you minus, because what are we going to do to this difference? We're going to take this difference, and we are going to square it. So once we square the difference, it really doesn't matter if it's positive or negative, but very important, we need to then divide by expected. So you see observed minus expected, and actually I did it in the correct order for once, divided by the expected 10.6457, and we get 0.5206. So I want to point out some important ones down here. Let's find an easy one. If you look at some of these, is there a really easy one? This one right here is really easy. What is the difference between 18 and 20? 2. What is 2 squared? 4. What is 4 divided by 20? 1/5. And look down there. Is that about 1/5? So let's look right here. Let's look at this one. If you round this to 13, what's the difference between these two numbers? Round this to 13. 6. And what's 6 squared? 36. And then if you divide, you get something like 3 almost, right? Does everyone see that? All you're doing is taking the difference. It doesn't even matter if it's positive or negative. This one right here, I don't know if there's any other easy ones. Probably this one right here is pretty easy. If you take the difference here, you get about 8. 8 squared is 64. 64 divided by 40 is about 1.5, right? 60 divided by 40 is 1.5. But does everyone see how I'm getting these numbers, how I'm getting the chi-squareds? The easiest one to look at is right here. What's the difference between these two numbers? 2. 2 squared is 4. 4 divided by 20 is 0.2, because it's 2/10. So that's an easy one to do right there. And that is just the formula, observed minus expected, squared over expected. These are all the cell chi-squareds. So we're good on this page. Next is the expected cell frequency condition met. Now, I want you to think about this for a moment. In this problem, we have 2 categorical variables. What was our original success-failure condition? We needed how many successes and failures? So if we have 2, how about we just say we need how many expected now? 5. We had 10 before. Now let's just say we need 5. That's kind of the way I remember it, is that we have 5 expected successes here is what we need to see. So we go back and we look to see if we have 5 expecteds. And technically, we only need to go to the smallest one, which would be right here. Does everyone see 65 and 69 are the smallest? So the smallest expected is 8.54, because this is the smallest number here, and this is the smallest number here. You're always dividing by the same number. So the smallest expected cell count would be from the smallest row and column respectively, and 8.54 is bigger. So yes, the smallest is 8.54. All are greater than 5. 8.54 is smallest. All greater than 5. 5 is something, it deals with the residual. There's actually a whole problem that mentions the standardized residuals due to, you guys remember that whole problem that mentions that the standardized multiple choice at the end, it's like standardized residuals might be questionable due to the expected cell count being small. Does anyone remember that? Yes. So if you want to know why 5, it has to do with the residuals, and you might get results that are wrong. But if you don't want to know why 5, just memorize 5. It'll always be 5 or chapter 22, categorical data. Always 5, chapter 22, categorical data. Sure. Let's look back here to see how we get the smallest. Actually, this is a different view of it. To get the smallest, since the math for this is row total times column total, and then the bottom is always grand total, right? So let's multiply the smallest numbers up top that we can. So I just go to the smallest row, or column, excuse me, and the smallest row. And then I line them up, and we already have the answer here, but I could do these two numbers times this over this. So I could do 69 times 65 over 525. And that would equal 8.54. So just find the smallest row, find the smallest column, over grand, multiply over grand totals. You're welcome. Good question. Now, this is the only time on the test that you will use wording for your null alternatives. This is the only time. And all you have to say, X and Y are independent of each other. X and Y are not independent of each other. That's it. You will know to do this when you see, and this is a good note to take, when you see a contingency table. That means you are doing a test of independence. This is the chi-squared test of independence. On this test, this is a dead giveaway for the chi-squared test of independence, chapter 22. You will also know because it's two categorical variables. We could technically not give you a contingency table. It would be a harder problem to write. It's easier to just give you the data in a table like this. If you have categorical data, you are going to use the null and alternative of independence. So we would simply write the null states, and we're looking at final major, right? Final major and initial major are independent. And then the alternative would state, and please write it all out, my handwriting is horrible, please ask if you can't read, are not independent, and I can't write. So the null would be final major and initial major are independent. The alternative would be final major and initial major are not independent. I'm on that. There's other ways to write it too. I wish on your guys' number was consistent at all times, so they make simple wording in each question. But they are independent, they are not independent. Just say X and Y are independent, X and Y are not independent. I'm good with the other way. Yeah, you could say Y and X, it doesn't matter, because Y and X will have the same relationship as X and Y. So they'll share that relationship. Good question. Okay, let's look at the results. Whoa. First thing I see down here is something we didn't ask you guys in this problem, the degrees of freedom. How many initial majors were there? 4. How many final majors? This is a 4 by 4. What's the formula for degrees of freedom? Rows minus 1 times columns minus 1. When you have this, when you have a 4 by 4, it turns into a 3 by 3. As in, let me show you. 4 by 4, delete 1 row, delete 1 column. What's left in the center? 3 by 3, right? You can do that there. Now, if you do this, make sure to not include the totals. These were not questions asked. This is a 4 by 4, not a 5 by 5. Do not include the totals. Rows minus 1 rows, columns minus 1, 3 by 3 left in the center. That's the degrees of freedom. It's kind of like n minus 1 and n minus 1 again, right? N minus 1 times n minus 1, because there's 2 variables. We've seen this before. So now, we go back over here and we see we have a chi-squared with 9 degrees of freedom. That tells us the specific chi-squared curve we would use, and then we landed all the way over here at 29. And if you notice, it says probability greater than chi-squared, so we need to shade above 29.077. The Pearson has your p-value, and that's what the graph would look like. And it would look way smaller than that. I drew the p-value way too big. Our p-value here is tiny. The chi-squared test statistic is found by doing what? To get this 29.077, what do we have to do? Add up all the individual cell chi-squareds. And remember, we were looking at the differences between the observeds minus the expecteds. And I want you to think about something for a second. If the null is true, we should get results where the what and what are basically the same. The null and the observed and the expected are basically the same, right? And then what's the top part of the equation equal to? 0. And when you square 0, what do you get? And when you divide 0 by something, what do you get? And when you add up all those zeros, what do you get? And that means we land all the way over here on the curve, and we shade to the right. And be careful, what's our p-value now if we land all the way over here at 0? Our p-value is 1. Because it's the probability of seeing our results or results more extreme if the null hypothesis is true. Isn't this the most likely thing to see if the null is true? So the further away you land, the more deviations there was over here, and the more unexpected this is if the null is true. If the null is true, something like this is the most likely thing, because the probability of this is 100%. Something like this are more extreme. Results like this are not as likely. They're pretty unlikely given the null is true. So if it's pretty unlikely that the null is true, what do you do to the null? Reject the null.
So which one should we circle?
So it says circle something. I circled a lot, didn't I? I'm very sorry. I get all excited. Circle that answer right there. The decision on whether to reject or fail to reject will be made on a p-value. P-value. Question? Through the Pearson measure p-value, the Pearson measure test statistic is the one where you add up all the chi-squares to that number right there, 29.77. You could add up all those self-chi-squares, and you get that number. The likelihood ratio is a little bit different than the test that we used to get. It'll always be the Pearson. Memorize the Pearson is the p-value. The Pearson has the p-value. Pearson has the p-value. And make sure it's the probability, because all p-values are probabilities. The probability of getting results greater than our test statistic. The chi-squared is a test statistic. It's not a p-value. You'll see on other tests tonight, you'll probably see like probability greater than t. So that's giving you the p-value, the probability of greater than our test statistic. Any other questions on this one? Question over here. Go ahead.
So in this problem, all we have to do is circle point.
State your conclusion in context of the problem. The conclusion in context of the problem is simply reading off the null alternative again. My conclusion is I reject that final major and initial major are independent. I have evidence to suggest that final major and initial major are not independent. All you have to do is say I reject, and say your null again. I have evidence, and say your alternative again. Very important there. Just say I reject, blah, 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 blah. Good.
So
Yes, and that's the other good way of putting it. If the P is lower than alpha, reject the null. And it's very important to always note the alpha level here of 0.05. It states otherwise. The P has to be lower than alpha. When the P is low, reject the hoe. What I hear. My stats 1 students tell me that. That's what they say. Below is additional output. Let's take a look right here. This output seems really confusing. Frankly, I avoid it, and I get what I need by just doing the math myself. When we look at down here, the bar height for A and the bar height for B, think about what we're looking at here. We're looking at biology, initial biology majors who went into engineering. Does that make sense? So initial biology majors. So we need to come up here, and we need to go to their initial major was biology. So we're in here. And then we need to match it to engineering. So we know our answer is one of these numbers. Well, I can tell you the answer is not 23 because that's the count. The total percentage is out of the total entire graph. Like if there's a big pizza, this would be about 4% of the big pizza. But when we look at this right here, this is the row right here we're looking at. If you notice, the row is biology. Do you notice how all of this stays in biology right here, right? So now when we look at this right here, we go to the row for biology, and we see that in the biology row, this is 8.85. Another good check is that the top one will be 50%. I think I can get this on screen. Do you see how this top one right here is about 50%. Does everyone see how 50%, my pinky, is pointing to this right here, that's 50. Then the next one down would be 10, and the next one down would be 30. Does it make sense that ours would be about 8.85? Does it make sense? So we are good on that.
Do you look at early percentage?
Yep, because if you notice, everything is in biology right here, and you notice this is all biology. If you want, watch me as I take this and I turn this like this. Do you see how I turned it? And then all the numbers would be going in the same direction. Does that make sense? Some people probably saw it visually. You can take it and turn it, and then now it's a column. You see it? Like it. So the next one over here, I mean, you could guesstimate this. We can probably figure this out pretty easily if we look at this and we say that's about 23%, right? Ish. So now we have physics and engineering. Physics and engineering, it's going to be the same sort of thing. And look at that, 22.89. Now, if you notice, you might want to put 23.46, but I'll explain why it's not that. I cannot write. So if you look at the other right here, if you trace across, the other has a lot more than 12%. Does everyone see this row right here? Is this, I'm going to circle it on here for you guys. This row of numbers is equivalent to this row of numbers. We have 1, 2, 3, 4, 1, 2, 3, 4. Match up all the numbers, double check your answers, make sure they make sense. Because it would not make sense if that number 4 was 12.70. That would be a wrong answer right there. Double check your numbers. Fill in the blank. Wow, we left one last thing off. If someone's initial major was biology, they seemed what to transfer into engineering as compared to people that had the initial major in the other 3 categories. So if someone's initial major was biology, and if you look, the people who were biology, were they more or less likely to become engineers at the end? Less, because that bar is lower. And this is kind of how the relationship goes. It's just looking at it more in depth. Okay. Any questions on this one? Now I will say this, you can do this whole problem on the calculator doing the chi-squared, but I would highly suggest this is where the calculator is probably going to take you longer. I would not suggest calculator on this. And it's a good double check if you have time. Questions? Okay, question number 3. Toyota wants to be able to accurately state that its 2016 Toyota Camry exceeds an average fuel efficiency of 34 miles per gallon. Automatically, we learned something about this problem right here. We're measuring miles per gallon in this problem. Quantitative or categorical? Quantitative. How many miles per gallon does it get? Quantitative. How many miles per gallon does it get? So this tells us quantitative. They tabulated the fuel efficiency of over 28 fill-ups. That's N. I don't know why we said over. The average fuel efficiency was 34.4. What in notation is 34.4? What kind of mean? Sample mean, and what's that in notation?
Y bar.
Y bar. And a standard deviation of 1.4. What's that in notation? S. As soon as you say Y bar, you will see an S. If you say S, you will see a Y bar. This is where we leave P, P hat, Q naught, and all that stuff by the wayside. The observed average from this study is indeed larger than 34 miles per gallon, but are the results statistically significant? Let's conduct a hypothesis test. The null states, and if you have Y bar, you have a sample mean. A sample mean is trying to give you insight into the what mean? The mu, the true mean, the population mean. So the null states that the true mean miles per gallon is equal to 34 miles per gallon. Can't think so. The alternative states that the true mean with the problem. So they want to know, I think, is it larger? But are the results statistically significant? It is larger than 34, but are the results of it being larger statistically significant? So if they're testing to see if it is larger, we need to test to see if it is larger. Read out your null and alternative to make sure it makes sense. The null states that the true average mileage these cars get is equal to 34 miles per gallon. The alternative states that the true average mileage these cars get is greater than 34 miles per gallon. Be able to read it as a sentence. Very, very important. Write that down. Read your null alternatives as sentences. Calculate the value of the test statistic used in the hypothesis test. So we've already labeled this as quantitative. And do we have one mean or two means? We have one mean. So when you see this over here, we go to our formula page. On your formula page, you'll see things that help you out nice and neat back here. We are doing something with one mean, and we are doing a statistical test. It said test it, and we have one mean. Very important to note how many samples you have and if it's quantitative or categorical. Before we were down here in the test of independence using these formulas right here. We saw this a moment ago. But now we're just doing one mean. So we have one mean. It's testing one mean. So let's go back right here. So much writing. So here we are. The formula being, we need to take the sample mean minus the hypothesized mean over the standard deviation over the square root of n. Now I want to throw something back to you guys here. Does anyone remember how to do a z-score? Z-score was simply observation minus mean over standard deviation, right? Do you notice any similarities between your formula now and that old formula? It's basically the same. All you're doing is taking a difference and then standardizing that difference, right? Look at the other formula in other chapters. P hat minus P naught, that's just a difference, right? And then what do you do to that difference? You put it over this right here. So you notice the other formula right here that gives you a z-score, and these are not the formulas for this problem. This one is over here. But you notice that's a z-score, that's a z-score. All a z or t or anything is a difference standardized. All we're saying is how far is this away, how far is it away, and then standardize it. But since it's for a mean, we have to do a standard error of the mean. That's why we're doing it for the sample size, where originally it was just a sample size of 1. So I mean, if you put right here over the square root of 1, that doesn't change it, does it? Could have been the formula all along. So good stuff. So forget those for the moment. Let's put this in right here. We want to do y bar. 34.4 minus 34.0 over s, which is 1.4, over square root of n, which is 28. And so the top part of that formula is 0.4, and the bottom part, 0.4, and then the bottom part of it is to square root of 28. .26 And once again, everything we've done right here by filling this all out, all this math that we've done, on the screen here next to you, this is a t-test right here. So if you go over to stat, t-test, you can enter in all of your data under here. You could enter in your hypothesized true mean of 34, your sample mean of 34.4, the calculator calls it x-bar, your sample standard deviation of 1.4, your sample size of 28, and you are testing if the true mean is greater than the hypothesized mean, and you can even hit draw, and it'll give you the curve and everything. We should get 1.511. Oh yeah, calculator. There it is, 1.511.
So this.
That's t-test right there, and I'd accept those results. You just got to make sure you do everything right. The biggest part of this is identifying the problem. You can put it into the calculator if you identify it. So the t-test right here gets us the same result and shows us the curve we had. If you notice, right here on the calculator, that mark right there is 1.511, and the reason we're graphing to the right is because I chose the null, or excuse me, the alternative of greater than. If you notice that points to the right, so we shade to the right. Probability of our results or results greater than our results is 0.0711. Good stuff right there. T-test on the calculator. T-test. The appropriate distribution, since it's a t-test, is the student t. Because Mr. T is what? He's mean. Mr. T is mean. When you have means, it's the t distribution. Remember that. Mr. T is mean. Someone's going to say that to themselves during the test, hopefully. As long as the shape of the data, the sampling data is what? Approximately normal or nearly normal. This is a big thing right here, because you notice the shape of this right here is normal. So we need the appropriate initial data to be nearly normal. So that's an assumption when we talked about this earlier, if we have one quantitative variable, we're looking at the nearly normal condition. One quantitative variable is the nearly normal condition. If it was two quantitative variables, it's still there, but we have to check it for both of them. Both distributions would be checked for the nearly normal condition. If it's quantitative, it's nearly normal. But if it's just one, you only have to check it once. But if it's two quantitative variables, like in chapter 20, it'd be check the nearly normal condition twice. It's still just the nearly normal condition, but you'd have to check it that group 1 is nearly normal and group 2 is nearly normal. So just check it twice. Look at this. Could it be any better for us? Go right here and go to 1.5. I would even put in a t with 27 degrees of freedom equals to 1.5119. Our sample size was originally 28, right? So for a one sample t, the degrees of freedom are n minus 1. One sample t, degrees of freedom n minus 1. One sample t, degrees of freedom n minus 1. I think mark your test statistic on the curve and shade the appropriate. They'd probably just accept this right here, just shaded like that. But I like to give the extra details. The p-value is this, technically. What is your conclusion using a typical 0.05? When the p is high, let it fly. So all we need to say right here is the p-value is too high to conclude, and I would just state it for myself just the normal way. I fail to reject the null. I do not have evidence for the alternative. Does that make sense? I fail to reject the null. I do not have evidence for the alternative. So I have to say it's high, so it's either B or D, right? Higher than alpha. To conclude that the actual is larger. It's too high to conclude that. So the p-value is high enough. No, it's too high. The p-value is too high to conclude that the average field efficiency is larger. So in other words, this one right here, it's too high for us to have evidence for this. Because when it's low, we have evidence for the alternative. Does that make sense to everybody? When the p-value is low, you reject the null, and you have evidence for the alternative. The p-value is just how likely our results are given the null is true. So if we get p-value 1 with the null, is it really likely to get what we got? Where did we land in our sample if we get a p-value of 1 for this test? Actually, we can't. It's not a two-test test. What's the highest p-value we can get? I guess we can get some above. If this was a two-tailed test, where did we land with the highest p-value? No. 34. If it was a two-tailed test, and you were to land right at the center at 34, you'd put right here, and then you'd shave the whole curve. Isn't 34 the most likely thing to see if the null is true? We'd have no evidence that it's different than 34 if we found 34. Does that make sense? Yeah. And that's why you would not reject the null. A high p-value means what you're seeing is likely given the null is true, so you would fail to reject. A little bit good right there. So fly bar equaled right there. Then the t27 would equal 0. So that would be that. And our test would be a p-value of 0.5. Any questions on this one? Questions. Go ahead.
Why is it too high, not high?
So I don't like the wording on this. I just don't like when we make these multiple choice. So the idea of too high, what I would like it better to say is it's too high to reject the null. But the p-value is higher than the value of alpha. So when the p-value is higher than the value of alpha, what do you do to the null? Fail to reject the null. When the p-value is lower than the value of alpha, you do what? So we should say the p-value here is too high to reject the null. We do not have evidence to conclude that it's greater than 34. That would be better. That'd be better wording. The p-value here is too high to reject the null. We will continue to believe the null. We do not have evidence for the alternative that it is greater than 34. When the p-value is low, you have evidence for the alternative. To make it very, very clear, these words go together. Reject, null goes with evidence for alternative. The wording fail to reject or do not reject fail to reject goes with not enough evidence for the alternative. We did not have enough evidence for the alternative. So we reject the null. It's because we're now believing the alternative, right? If we fail to reject the null, it's because there was not enough evidence for the alternative. So when you fail to reject the null, what do you believe? You don't reject it. You believe the null. If you reject the null, what do you then believe? The alternative. So you can only believe one at a time, right? So when you say I reject the null, you have to believe the alternative, then I have evidence for the alternative. If you fail to reject the null, you continue to believe it, and you do not have enough evidence for the alternative. So you can only use these pairs of wording together right there. Reject means you have evidence for the alternative. That's why you're rejecting. Doing great on time, everyone. Continued. Oh, no, they put it in that order. Someone didn't stack their histogram. The p-value for this test right here is only accurate if the distribution of fuel efficiencies is nearly normal. Here's a histogram, and we've got a QQ plot based on a sample size of 28. Can we say the distribution is nearly normal? And the answer is yes. I think they say, how did you come to this conclusion? The answer is yes. The p-value right there, you could mention this is basically straight. This is basically unimodal. But this right here is very important. This is the goodness of fit test. The goodness of fit test is to see if it's normal. What does the goodness of fit test assume to start out? What is the null for goodness of fit? Then what? Just what's the null in words for it? Or this we feel forget the goodness of fit test. This is a test we don't use that often. The null is that the data is normal. So do we reject that null right here? No. So we're gonna keep with the null that the data is normal. We've done that a lot on this test. The null on this test, don't think of this as a test like it is a hypothesis test, but it's not like you're testing a means test. This is something we did in chapter 6. It's going back way back when. Remember we had the fat pencil test, and so that up there is the fat pencil test. So we had look at the histogram, see if it's mound shape. We had the fat pencil test. Did they all fall in a straight line with the line bent? And this is just all this is doing is just seeing if the data is nearly normal. So we assume it is normal down here. The null is that this is normal. The alternative is that it's not normal. And I know this is crazy. It's a hypothesis test inside a hypothesis test. Does that make sense? Because to do your test on the mean, the data needs to be nearly normal, and this is just a check to see if it is nearly normal. It assumes to start that it's normal. And then if the p-value is low, as it says right here, you will reject the null that it's normal. So you start out believing it's normal, so you have evidence otherwise. For anyone who goes on in statistics, this is how we do any sort of statistical test for conditions. You assume you're good on a condition, so you have evidence that you're bad. So we want the data to be normal, right? So we assume the data is normal to start. The null is that the data is normal. That's right there. Can we reject that null? No, p-value is too high. So are we good? Yeah, good. You're good. Does that make sense to everybody? As it says, the null states the data is from the normal. Small p-values reject the null. That p-value small, do not reject that null, so the data is what? We are good. The data is normal. And reread this if you see this on your own test. This is just to get condition 3 nearly normal for quantitative data. That's all this is. This is not a test of means or anything like that. It's just to see if the data is normal. It's condition 3 for quantitative data. So we're good. You could say that the goodness of fit test tells us that the data is normal. The goodness of fit test suggests to us that the data is normal enough. Circle the alternative that best completes the statement. A p-value indicates, what did we write on this? The probability of the observed data or data more extreme than that, given the null hypothesis, is true. And I think that's the right answer. Let's check. The probability that the null hypothesis is true. Well, we need to talk about our observed results. The probability of the observed results or results more extreme given the alternative is true. No, that is not right. And the probability the alternative is true. Nope, it is answer A. And you could write, I want everyone to look at this definition right here because this is really accurate. Whenever you interpret a p-value, the probability of my observed results, like let's look at our problem we had before where we got an observed result of, we had 1, 2, 3. If everyone remembers just a little while ago, this was our observed results on the last problem. So the probability of my observed results of a sample mean of 34.4. Does everyone see what I just said my observed results? Or results more extreme than that, in this instance, greater than, given that the null of 34 miles per gallon is true, is 0.0711. I just gave the numbers in that interpretation. So if you have to interpret a p-value, the probability of my observed sample mean of 34.4 or results greater than that, given that the null hypothesis of 34 is true, has a probability of 0.0711. 3 things right there to interpret the p-value. That is a p-value right there. Oh, this is a fun page. When it comes to type 1, type 2 error. Kane, I'm going to give you a hard question. Kane, will you count for me? Go ahead and count for me, Kane. 1, 2. Who wants another hard question? Who wants a hard question? Anybody? Go ahead and give me the give me the letters of the alphabet. A, B. Who wants a hard question? Early, someone close to the front. Ready? What are the sides of a battery? Sides. Plus and minus. So now when we do type 1, type 2 error, I want us to remember this. 1, 2, A, B, plus, minus. I find it a lot better than that 2 that I can't remember what goes in what box. What does this all mean? A type 1 error is a false, type 1 error is a false positive. A type 2 error is a false negative. If I increase alpha, I increase my what? It's connected directly to my what error? If I increase alpha, I increase my type 1 error. 1. If I increase beta, I increase my what? That's 2. Alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. Keep these all connected. Now what is a type 1, type 2 error? Now let's do this right here. Who's not in my class? Do you wake up every morning and think that you're pregnant? Okay, so what's the null hypothesis? Okay, so what is the null hypothesis on this? The null is that you are not pregnant. And I mentioned this because, well, Anyone ever see a pregnancy test? It has a plus for pregnant and a minus for not pregnant. So when you think about prayer, so let's have what's up. Now, if you have a false positive on that pregnancy test, what does the pregnancy test tell you? Wait. If you have a false positive on the pregnancy test, what does it tell you? False positive. What does it tell you?
You're pregnant.
If you are pregnant, what are you? No. If you have a false negative, what does it tell you?
You're not pregnant.
But you are pregnant. Now, what do you think of Samoa? Because let's think about this in other terms. Is it fair for me to assume everybody in this class is a cheater? Cheating on the test. Hey, you are cheating. What is the null for when it comes to students cheating? That they? No, what's the null? You're not cheating. The null. Like if you're thinking about a false positive, I want to listen up closely. A false positive is whenever we say we have evidence for something that would take evidence to think of, right? You don't say, I'm pregnant. Someone will say, well, how do you know, right? Anything that takes evidence is an alternative, right? Does that make sense? You say, I'm pregnant. Someone says, why? You say, I don't know. Just because. That's weird. If I say, you're cheating, would you want me to have evidence? Do I need evidence of you not cheating? No. It's just what I assume, right? That's what a null is. A null is whatever you believe, just you don't need evidence for. Nulls are great. It's all the time. Okay? What's up? Null hypothesis. You're not cheating. So with that in mind, when we make a false positive, what do we do to the null? Because if we have evidence, we want the null. In a false positive, you could write this right here, down at the bottom if you want. You reject null down here. And you fail to reject down here. This is what you do to the null. Because you can think of evidence or positive as evidence for the alternative. Just remember the example we talked about right here. When you have a false positive on a pregnancy test, there's evidence you're pregnant. The null was you are not pregnant, so you have evidence for the alternative there that you are pregnant. If I go to a student and say they're cheating when they're not, I have made a false positive, a type 1 error. So let's look at these examples here. When we fail to reject a false null hypothesis, so now we did not reject the null. Did we find results if we fail to reject the null? Did we find results for the alternative? No. So we have made a what error here? Yes. We failed to reject a false null, so we should have rejected it. The null was false, and we should have rejected it. Does that make sense? If the null is false, should we reject it? If it is false, we should reject it, but we did not. When we reject a true null, so if the null is true, should we reject it? No. We have made what? This is when we find evidence for the alternative, and we shouldn't have. If we increase the type 1 error rate, alpha, from 0.05 to 0.01, 100, what effect does this have on type 2 error? They're inversely related. If you make a type 1 error more often, you will make a type 2 error less often. You want to see me ever make a type 2 error? In our cheating example, what is a type 2 error? What is the null for people? That they are what? Type 2 error is what I'm saying they are what? Correct. Is everyone here that in our example I'm saying they're not cheating when they are? I'm going to use a very powerful test and they never make a type 2 error. That is to say you're not cheating when you are, right? Watch this. You're cheating, you're cheating, you're cheating, you're cheating, you're cheating, cheating. Did I make any type 2 errors? I did. How do I make a type 2 error? I have to say you're not cheating when you are. All I did was increase my alpha to 100%, and I rejected the null on everyone. If you increase alpha, because if you reject the null, you can't not reject the null. Does that make sense, everybody? To make a type 2 error, you have to fail to reject the null when you should. But if I reject the null every time, then I would never make that mistake. Of course, is that really a good idea? Yeah. It's probably not a good idea. But when alpha goes up, beta goes down. When alpha goes up, beta goes down. If we increase the type 1 error rate from 0.05 to 0.10, what effect does this have on the sample size? None. Nothing was said about sample size. Sample size is its own thing. If we increase the type 1 error rate from 0.05 to 0.10, what effect does this have on the power of the test? Now, if you heard what I said, I had a very powerful test to find cheaters. Cheating. Is that a very powerful test? Will that find all the cheaters? It's a good test, but it's very powerful. If you think about that, power of the test is very important because you might want a test, like if we were looking at, let's say I get sick in here and coughing myself to death. If we have like an Ebola outbreak, would you want a very powerful test that would figure out who could have Ebola, or a test that could make type 2 errors? A type 2 error would be what? Should you assume everyone has Ebola, or what's the null? The null for Ebola would be what? That you're healthy. So a type 1 error would be to say that somebody what? Has Ebola, we reject Ebola, they're healthy, we have evidence that they have it, right? A type 2 error would be what? You let them know they do have it. So if I had a powerful test that accidentally saw too many people as having Ebola, and we said that, we would catch all the people who had it, because we would be a little bit too careful. And here's the thing. You think about how the medical industry works. The medical industry works is that it might give you a really powerful test to start. And it might just be like a saliva swab or something, right? But then what do they do next? They give you a blood test. Sometimes the better tests are more invasive. But they might have a test to start that is a very low threshold, a very powerful test to identify all the possibilities, and then use a better invasive test. But do they want to plug everyone in for a spinal tap right away? Payne says no. So that's why you see that right there, a very powerful test to start in the medical industry, and then sometimes a more invasive test that does better results. So what effect does this have on power? This will reject the null more often, because alpha is type 1, and we will reject the null more often. Suppose we create a 95% confidence interval using the same data. We decrease the level of confidence to 90% and create another confidence interval. What effect does this have on the width of the confidence interval? So we go from 95 to 90. We will see narrower. If we increase the sample size, what happens to the type 2 error rate? And this is a really good question right here. And it's what a lot of researchers need to know, is that when you want to make errors less often, you can increase your sample size, and this will decrease your error. So increase sample size, decrease type 2 error. There are 3 things that increase the power of our test: sample size, effect size, and alpha level. All these 3 things right here, if you increase them, which you can't really increase effect size, but all those 3 things will increase the power of a test. Just as a quick review right here, the power of a test is the ability to reject a false null. My friend's coming into town this week to play basketball against me. My friend Kobe just retired. He's going to play me a pickup game, a little one-on-one, and we're going to see who's better, me versus Kobe. Now, when we start the game right here, I'm already sick and I can't win. If I play Kobe for 30 minutes, it's going to be pretty easy to see who's better. What if I play it for 30 seconds, or 3 seconds? Grab the ball, I'm going to see who grab the ball and just throw it at the hoop. That's it. That's a great talk, right? Well, when is it easier? If I play it for 3 seconds or 30 minutes? Let's say, when you're down to a Kobe practice, pretend you don't know Kobe. Just some random guy. Although he's way more athletic than me and taller and all that good stuff, and thinks you can guard basketball. Who ran it down and play basketball. And you only need to see 3 seconds of our game versus 30 minutes of our game. When is it easier to distinguish who's better? 30 minutes. That'd be much. Well, what am I increasing right there? Sample size. And that means your test is more powerful, because your powerful test is being able to distinguish, because the null would be that with the same ability. The alternative would be that one of us is better. Does that make sense? 2 random people. Null is that we have the same ability, because I don't know who they are. Alternative is one of us is better. We increase the sample size, it's easier to see who's better. Now let's talk about effect size right here. If I take on Kobe versus me, it's easy to see who's better. Who else here sucks at basketball? We play each other at basketball. You and me. It's going to be easy to see who's better at basketball. Know myself too. So with this in mind, we play each other, and the difference is a lot smaller. Do you think it's true that one of us is better? But it will be harder to see who's better between the two of us versus when I play Kobe, because what have I changed here? What have I changed in this example? The sample size, we're going to say 30-minute game, you and me, 30-minute game between me and Kobe. So I look talent, the difference between the null that we see talent, the alternative that there's a difference in talent, that's the effect size. The effect size is the true difference between the null and the alternative. Because between Kobe and I, there's a big effect, right? Way better. Between you and me, there's not that much of a difference, but there might be one. Any of these increases power. As you notice in our example right here, if we reject the null more often, the test is better able to find results. In layman's terms, a powerful test that rejects the null finds results. That's in layman. Power, by book definition, is the ability to correctly reject a false null. That's the book definition. But in layman's terms, a powerful test finds results. It rejects the null and finds results. So, the ability to correctly reject a false null is power. The formula for power is 1 minus beta. If you look at that, 1 minus beta is everything but making a type 2 error. As in, you don't fail to reject the null when you should. So we're able to correctly reject the false null. Dude, go over it again real quick. 1 and 2 stands for type 1 error, type 2 error. A and B is alpha and beta, which are connected to 1 and 2. If you raise alpha, it literally is a type 1 error is your alpha probability. And beta is literally a type 2 error. Alpha and beta do not equal to 1. But if alpha goes up, beta goes down. They're inversely related. If beta goes up, alpha goes down. Plus minus means false positive, false negative. Positive means you have results. That's important to know. It means you have results for the alternative, evidence, positive evidence. So when we think about the null, as we talked about, the car gets 34 miles per gallon. If we have a false positive, we're saying we have evidence it gets more than 34 miles per gallon when it doesn't. But if we have a false negative, we continue to believe the null. We don't have evidence or alternative, but we should have rejected the null. So, and down there at the bottom, you see down here with positive evidence, we would reject the null. With negative evidence, we don't have evidence to reject the null, so we stay with the null. We fail to reject it. Question. Good. Effect size is the true difference between whatever you're measuring. It could be that this car actually gets 35 miles per gallon. Imagine this. The null was that the car gets 34 miles per gallon, right? What if we're actually doing like a Tesla and it gets 60 miles per gallon? Is that going to be easy to notice? Yes, because that's a big effect size, right? That's an effect size of 26. Well, what if we're testing like a new Toyota that only gets 34.1? Is it true that the car gets more than 34? But it only gets a tiny bit, right? Is that going to be easy to notice that it's a little bit more? No. You see the effect size is smaller. The effect size is the true difference from the null. So if the car actually gets 34.1, that's hard to notice with 34. If it actually gets 60, that's going to be very easy to notice, right? So, and of course, no matter how many cars we sample, and also at what point we're willing to reject the null. All those things control the power, the ability to correctly reject the false null. We are getting to the home stretch of this. We'll finish right around 10. Let's do a 2-sample T right here. If you notice, we have 2 goodness of Fisk tests. We have bombs away and Applebaum laptops. We want to test these 2 laptops to see if there is a difference between how long it takes them to be booted up, or maybe something like that. The amount of time until the laptop stops working. The question asked here is how long until the laptop stops working? What kind of question are we asking? Very important. Quantitative. And what you'll notice is we are doing how many means? 2 means. This is chapter 22. 2 means chapter 22. The 4 conditions. 3 of them are listed below. Indicate which one and which condition is met. So I think we just want you to label 3 out of the 4. That's nice of us. Condition 1, random, randomly selected laptops. Problem should state they're random, and it does. You're good. Condition 2, we need to sample less than 10% of all laptops. As long as you get that, you're good. Condition 3, nearly normal. Careful, because it's quantitative. If it's quantitative, it's nearly normal. To check to see if it's nearly normal, they're having us do the check right here to see if this is our previous test we just did before, which the null is that the data is from the normal, and this is for the bombs away and for the apple bombs. These distributions are normal enough because we don't reject them being normal. The null is that they're normal. We do not have a p-value small enough to reject the normalcy. So we fail to reject that they're not normal. We're good. Finally, condition 4, independent means. Question in 2 seconds. So it is that the 2 means are independent of each other. I do not think these 2 laptops groups would influence each other because we're testing this laptop and this laptop. It's not like we're saying, let's test the laptop, let's test the hard drive of the laptop and see if it burns out, and then let's test the motherboard of the laptop. Because the motherboard of the laptop and the hard drive might be dependent. We tested the same laptop twice. That'd be dependent. Does that make sense? We said, well, now let's go to stress test after this. The same laptop, but these are different means. You're talking about the nearly normal?
Yeah.
In the nearly normal, I hate this condition because I never think we let you guys know it properly. If we fail the nearly normal, there are 4 ways to check the nearly normal. Let's turn the sheet sideways. The nearly normal can be checked 4 ways. Everyone listen up. Way number 1 to check the nearly normal is to look at the histogram. If the histogram looks good, you're good. If the histogram looks skewed, you're bad. Way number 2 is to look at the QQ plot, the normal probability plot. If it looks straight, you're good. If it looks bent, the more bent it looks, the worse you are. If it looks bent of some sort. And that's the fat pencil test. Way number 3 is with the p-value on the goodness of fit test. If the p-value is above 0.05, you are good. If the p-value is below 0.05, you are bad. And this is probably the most likely way we will test you on it. That's probably the most likely way. So if the p-value, as you see there on the goodness of fit test, is above 0.05, you're good. Below 0.05, you're bad. As it says, low p-values reject the null, that it's normal. Now, way number 4 is actually the way that I like, which is you would need to look at the original shape of the histogram and use the large enough n condition. The large enough n condition states that the new distribution of means of sample size n will be normal enough given the original shape of the distribution meets certain criteria. And that's a longer explanation, which we don't use so often on this test. Read over the large enough n condition again. I don't know if we're going to get into that, and it might only be worth 2 points. So if you want to read up on that, do. We're most likely going to use probably this on the test. Not saying it's not important, but it's the large enough n condition mentioned in chapter 16. Chapter 15, excuse me. Chapter 15, large enough n condition, which carries over to this chapter for means. So do you remember that one a little bit? Like, do what? Like if the original distribution is extremely skewed, n needs to be greater than 100. If it's a little bit skewed, n needs to be greater than 30. It's normal, any n works. So look at the original shape of the distribution. The larger n is, the more normal the distribution means. The sample size n will be. So, the large enough n condition. The larger n is, the more normal the distribution means. The sample size n will be. If the original distribution is extremely skewed to the right, n needs to be extremely skewed. Extremely skewed, n needs to be greater than 100. A little bit skewed, n needs to be greater than 30. If it's normal, n is something and it's not a these are not, real quickly, these are only to check the nearly normal condition. These are not the 4 conditions here. These are just the nearly normal condition. The 4th condition for the conditions on this is the independent means. Both means are independent of each other. These were all part of the nearly normal. Here we are, write the appropriate null and alternative hypothesis. Since we are testing two means, the null states, and we have bombs away versus apple, and you'll notice down here you can write your null and alternative by just putting mu, mu. Does everyone see this? I put two mu's before this. And even right in here, equal to 0. Right there, you've written the null and the alternative. If you see this output where it's something minus something and it's a t-test, I have written the null and alternative right there. Excuse me, just the null. There's the null. The null is that the true mean of bombs away minus the true mean of apple bombs is equal to 0, that there's no difference between those means. So let's go up here and write the null bombs away minus the null, the true mean apple bombs equals 0. And right out to test that whether one brand lasts longer, it does not give preference. And it does not say which one should last longer. And I'm just doing subscript down there for the null, the null states that the true mean of bombs away minus the true mean of apple bombs is equal to 0. The alternative states that the true mean of bombs away minus the true mean of apple bombs is not equal to 0, as in there is a difference between those means. If you notice, I wrote it out down here at the bottom by just putting mu and mu equals 0. That's the null right there. You can write it out just for yourself like that. This is chapter 22, difference between two independent means. Using the output below, what is the appropriate p-value? Now, if you'll notice this right here, you have your greater than, your less than, and that makes this one the does not equals to. So the alternative right here that we're looking at is this one. And what you can do to check is if we wanted it to be less than, you could put less than right there for the alternative that bombs away, the true mean of bombs away is less than the true mean of apple bombs. You could actually just put that in there right there. You can also write it where the equal sign is between them. Another way to write the null alternative. But you could substitute in this alternative right there, but this one is the does not equals to, because it's the two-tailed. It's the does not equals to. P-value is, it goes in the order of does not equals to, because greater than the absolute value, so the value of this is negative 3.23, and over here on this side, well, shouldn't mark it that high, 3.23 is negative 4 greater than the absolute value of negative 3.23. What's the absolute value of negative 3.23? Is 3.23. So what's the absolute value of negative 4? Is that greater than that? Is 4 over here greater than the absolute value of that? Yes. And you see, so that's results that are does not equals to, because it's results more extreme. Because if we do the less than, if you plot less than this, you see how there's very little area, and that would be 0.0226, and you go less than this line. And if you go above this line, you basically shade in everything, right? But then the does not equals to is double the smallest. So this area right here is 0.0226. Also over here we have 0.0226, because you would just double that area, and that's what you get right there when you have the does not equals. It's the two-sided double. And so you notice the does not equals is double the smallest. If the test alternative is does not equals. If it is greater than or less than appropriate p-values, does not equals this one right here. And the does not equals is always double the smallest. Okay. In this particular study, what brand of computers had a higher average lifetime? Maybe. Here's how to know. The equation right here, bombs minus apple is negative. Does everyone see this? Bombs minus apples is negative. So if these numbers were 7 and 10, would it be 7 minus 10 or 10 minus 7? Does everyone see that 7 minus 10 is negative 3? So which one is bigger? Apple. Substitute in, because this difference right here is telling you when you subtract these two numbers So put in fake numbers. Round that to 3, and then say, oh, 7 minus 10 is negative 3. Thus, Applebaum's had to be bigger. I know those aren't the real numbers, but just pretend for a moment. 7 minus 10 is negative 3. Thus, Applebaum's was the bigger one. Using a 5% significant value, state your conclusion. Do we reject the null? Yes. And just read it off. You need to write down, I reject the null, that the difference between, the true difference between the mean of Applebaum's and Baum's away is equal to 0. I have evidence that the true difference between the mean lifetimes that the true mean lifetime these computers get is different than 0. So I reject the null that the true mean difference in lifetime between these computers is equal to 0. I have evidence that the true mean lifetime difference between these computers is not equal to 0. Sure. I reject the null that the true difference between
Can we just write I reject HO?
no. I reject the null that the true difference between mean lifetimes of Baum's away and Applebaum's is 0. I have evidence that this difference in mean lifetimes is not 0. Not 0 means does not equal 0, right? And make sure you notice I mentioned the computers, and I also mentioned the variable in question right here. I said in mean lifetime, right? Measuring like average lifetime. That's just sample size coincidence, yeah. Coincidence. That is interesting, though. I reject the null that the true mean difference, or the true difference between mean lifetimes and Baum's away and Applebaum's is 0. I have evidence that the true difference in mean lifetimes is not 0. Good stuff. We'll finish right around 10, everybody. And here we are with another 2-sample T, and this question is definitely giving people a run for their money. Question? Austin? What is it? Yeah. Yes, you should. When you say you reject the null, that should always be followed up with, I have evidence for the alternative. You say I reject the null, I have evidence for the alternative. So I reject the null, stated in context of the problem. I have evidence for the alternative, stated in context of the problem. Yeah, even though it's obvious, like roughly, yeah, reject the null, we have evidence for the alternative. So definitely get that. So yada, 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 90% confidence interval. This problem isn't bad at all if we know how to work our 90% confidence interval. When we make a confidence interval, the confidence interval has a center that is the difference. Now, we don't really get to know much of this problem. And man, they're definitely making it tougher by not telling me the degrees of freedom. I could assume a lot. But I want you to know something. If you take the upper plus the lower of a confidence interval and divide by 2, what do you get? Close. Huh? Think about this. I'm going to spend between $6 to $10 on lunch computer. Use that for lunch tomorrow. I'm going to spend between $6 to $10 on lunch tomorrow. Use that formula right there and see what you get by doing the formula. You get 8. What is 8? The center of that interval, the mean, right? Does everyone see this? So 6 plus 10 equals 16 divided by 2. So this is the center. Now, what do we get if we do upper minus lower divided by 2? That's the margin of error, right? Because if we do 10 minus 6 divided by 2, we get 4 divided by 2 is 2. So these are important formulas right here. Also, upper minus center equals margin of error. 10 minus 8, center minus lower equals margin of error. Who knows what formula could come in use? But just 10 minus 8 equals 2. 8 minus 6 equals 2. Just gives us margin of errors.
Standard error, margin error.
Nope. Standard error is one part of a confidence interval, especially in doing sample statistics. The standard error times the test statistic is the margin of error. Like t times the standard error. Like standard error of a times t is equal to the margin of error. This is one part of it. Good question. Okay, circle the best choice below. Let's check some of these. If we do 0.92 plus 0.46 divided by 2, we get 0.69. That is the difference. But I want to point something out here. We are able to reject, what do? We fail to reject the null right now, right? However, this output does allow you to determine which interval could be correct. 90% confidence interval, all but one of these intervals can't possibly be the 90% confidence interval. That was erased. So one of these can't be it. So the one that can't be it is going to have a few requirements in it. This interval right here, we are saying that the difference is probably somewhere between 0.46 to 0.92. Does this tell us the difference is different than 0? 0 in that interval. 0 is in that first interval? It's not. So would we be able to reject 0? We would. It's not an interval, right? I'm saying I think the difference is between 0.46 and 0.92. I don't think 0 is the difference. Does that make sense? So anything outside that interval I can reject. But over here, do I reject? No. So we need something with 0 in the interval. Does everyone see that? Since we fail to reject over here, we need 0. So that automatically makes that one wrong and that one wrong. Next, we test this upper plus lower. There. Upper plus lower. This is a minus. Divide by 2. And that's 0.69. This might be the right answer. And upper plus lower. Divide by 2. That's not going to be the right answer. And upper plus lower. Divide by 2. Sure. What I'm doing is so everyone listen up. What I just did right there is I checked the center of all the intervals. What should be the center of these intervals? The difference, right? Does that make sense? So the upper is that last number over there. The lower is the first number. So when I'm adding the upper and the lower and dividing by 2, I'm finding the center of the interval. What should the center of the interval be? 0.69. So the center of the interval, which is the difference, which is our center of the interval, which is our best guess, upper plus lower divided by 2 should equal 0.69. And only the first, and maybe the second one, I didn't check the second because well, it's not being negative, I think. But the first and the third had 0.69 at the center. So the interval must contain 0 and have a center of 0.69. Does that make sense? Okay. What? If the interval, if on a 2-sample test, if the test is insignificant, the interval will contain 0. On a 2-sample test, if the test is significant, the interval will not contain 0. Okay, on a 2-sample test, if the test is insignificant, the interval will contain 0. On a 2-sample test, if the test is significant, the interval will not contain 0. Because we're saying it's significantly different from 0 if it is significant. It will not contain 0. This test is insignificant, so our interval must what? Contain 0. That's what we narrowed it down a little bit. Then we check to see the center of the interval was 0.69 by doing upper plus lower divided by 2. Just finding out the average of them. We'll get done right on time, everyone. We're going to do it on this one just in time. Get done right at 10. The answer was C. The answer was C. Long question. For a particular operation, patients must be anesthetized, unconscious. At the particular hospital, a common drug is administered, yada, 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 knowing the average amount of time it takes for the drug to work. The next 20 patients, this drug is carefully monitored. How many minutes are taken for the drug to work? So what kind of problem are we working with right here? We're looking at how long the drug takes. Quantitative. But watch out, I think I heard quantitative. We just are looking at with patients how long the drug takes. We have 20 patients, so that's N. We have an average, that's Y bar. We have a sample mean or a sample standard deviation, that is S. So we've identified all this. To make a 95% confidence interval to estimate the true mean, we need to get the critical value. On the next page is a series of curves. N of 20 is very important. N of 20 gives us the degrees of freedom here. Degrees of freedom equals N minus 1. Going over to the next page. So we need a degrees of freedom of 19. So we're down to these. And now we need to make a 95% confidence interval correct. But if you notice, the confidence interval looks like this. It does not look like this. This box is checked right here for left tail. We want a confidence interval that shades the middle 95%. And our t-statistic is very close to what for a 95? It's very close to 68, 95. It's very close to 2. Does everyone see that? The correct answer is 2.093. Because it's 68, 95, 99.7. T is like the Z. It's not identical. It's going to be a number close to 2. And I know the other one's close, but this one is the right one because that's what we need there. Right degrees of freedom, we are good. So right degrees of freedom, right kind of curve for a confidence interval, and we are good. Now here's the problem. We could be really tricky on this. I want to make this clear. Just because this is checked doesn't mean it's the right answer. We could have done this. We could have changed this number to 0.975. And if 9.75% of the curve is shaded in here, what is left underneath this tail? And if you were to put that on the other side, you'd have a 95% confidence interval. Does everyone see how we could trick you with that? It's very tricky. Because this point right here only has 2.5 above it, right? That make sense? This point over here only has 2.5% above it, right? So it's the same point. If we put 97.5% below this, that leaves 2.5 above there. If we put 95% in the middle, it leaves 2.5 and 2.5, right? So that we could be really tricky. Watch out on that because down here you've got basically the same thing. Does this say, this could say, it says 95 here, but if this down here said 97.5, it could be the right answer because then that leaves 2.5 above here and makes this 97.5%, which this would be at the same mark of 97.5, and then this would be at 2.5, running it that way. And you see how there's 95% in the middle. This is a really tricky way of asking it. Practice up if you're a little bit worried on it. That's just a really tricky way. Almost done. 2.09 was it? So we take our sample mean of 5.26 plus or minus 2.093, and we use the standard deviation 0.44 over the square root of 20. This is a one sample means confidence interval, also known as a t-interval. Go here to the calculator, and you can do it on the calculator, or you can go over to t-interval, go to your stats, enter in 5.26, standard deviation of 0.44, sample size of 20, 95%, and it would not have answered for you which one to circle, but it will give you the confidence interval of 5.05 to 5.47. So that's what that equation solves out for right there. That was T interval on the calculator. T interval. T interval. Mr. T is mean. The manufacturer of this drug claims it takes an average of 4.5 minutes for the drug to work. Does your confidence interval tend to verify or refute this claim? Your confidence interval refutes it. It is outside. I am 95% confident the true mean amount of time this drug takes to do whatever it's trying to do is contained in the interval 5.05 to 5.47. I am, state your confidence level, 95% confident that the true mean amount of time this drug takes is contained in the interval 5.05 to 5.47. Interpret your confidence intervals in context of the problem. We're almost done. We're almost done. During the business analytics presentation, we talked about what movie? Moneyball. We also mentioned what store? Target. They figured out that a girl was pregnant before her parents knew. True story. No joke. A state claims that the probability of winning any prize on a scratch-off ticket is 6%. So wants to verify this claim by conducting a hypothesis test. To have a valid hypothesis test, they would need to have a sample size of 100. What condition are we checking right here? You guys are right. I heard 10% can be used, random can be used, right? But what condition are we going to fail? Success, failure. If they have a win percentage of 6% and we take 100, how many expected wins would there be out of 100? 6. Do we pass the success, failure? If the NP naught and Q naught, you're right. So 10% is one of them. Random's another. Success, failure because it is, and that is false. So NP naught and NQ naught, we do not pass NP naught. If the null hypothesis is true for the chi-square test of independence, we would expect the observed values to be very close to the expected values. And that is true because if these are basically equal to 0, we add up a bunch of zeros and we land down here on the curve and we get a large p-value. The closer they are, the more probable it seems the null is true. It doesn't prove the null or anything like that. It just seems more likely. A two-sample t-test can only test a difference of 0 between two means. I think I wrote this. It is false. If you look at the equation on the sheet, the equation right here has 0 plugged in, but on your thing, on your sheet, it either's got like an alpha like or a delta like that, or some crazy Greek delta. Anyone here got to draw a delta? It's weird. But that can substitute in any value that you can test against. So we don't need to test against 0. That was maybe the most unfair of questions we asked. That was really a tough one. Probably a lot of people put in true there. But no, it can test any value. In a criminal trial, the null hypothesis is the defendant is innocent. Assume in one particular trial the defendant is actually guilty. The power of the test in this situation means the probability of correctly concluding that the defendant is guilty, and that is true because that would mean we reject the null, we find evidence of the guilt, and we do so. If you have questions, come and say hey to me.
These chunky ass candles.
Hello.
Do I have cards on me? Yes, you can take that. All yours. But if you want a business card, you want to get a hold of me, they're up here at the front. If you guys want a card, they're up here at the front. Here you go. Business cards at the front if you want to get a hold of me. Candy, anyone? Candy? Candy? Okay. Anyway. So the probability of observing a sample mean of 34.4 or higher, given that the truth is 34, the probability is 0.0711. So the probability of observing my sample results of 34.4 or higher, given the null of 34 is true, is a probability of, see it, Candy, Candy guy, Candy girl, Candy, Candy, Candy. There you go.
When
I gotta get rid of it all or I'll eat it. Do it.
increase the same size, do you also increase the type 1 error? Does all those three also increase the type 1 error rate?
No, increasing sample size actually won't change type 1 error. Type 1 error is only alpha. So type 1 error is simply alpha, and increasing sample size decreases type 2 error, though. Increasing sample size decreases type 2 error.
So what affects alpha?
What affects alpha? It's just alpha. You pick it. So you can just make your alpha whatever you want. Say alpha 0.05, alpha 0.10. Probability of making type 1. I have your pens.
Here it says the height
Yeah?
compares 0 to 0.25, so we put like 0.08.
Yeah, no, decimals work. You can, or 0.0885 works.
Over here it's from 0 to 1 instead of like 0.
We accept either way. So we're good either way. Yeah.
Thank you.
Yeah. Sure.
Explain me the Barbie. I'm pretty sure it's
The Barbie. So you see, we look inside of physics, and everything needs to be physics at all times and just engineering. So you see how this is all physics? And then we go here to engineering. And then, so this is the row of physics. You see how that's all physics if we look across the row? This is the row of physics. So that's the bottom number, so 22.89. And you can check it by saying, okay, these are people who started out in physics and went to engineering. So of the people in physics who went to engineering, so that would be 19, so let me double check here. They started out in physics and they ended up in engineering. Double checking, make sure I got this right. And so that'd be 19 out of the 83. So there are 83 people who started in physics. Does that make sense?
Yeah.
And then there were 19 out of those 83. And if you do 19 and you got your calculator, I think you got his calculator right.
28.
Hope you got his right. Yeah. Do 19 divided by 83. Oh, thank you. And 22.89 right there. It's the row percentage. You said 23.
Yeah.
It's the row though. 22.89. That's what I wrote down everything, right?
Yeah.
Yeah. See, this is the row where it says row because everything here is physics in the row.
Yeah.
Does that make sense?
Yeah.
And so you would want I know this isn't a row down here, but everything here is
How do you
physics.
know what to ask?
This right here because this says initial major physics. You see that right there?
Oh,
So and then max it up here, initial major physics. And then if you look at this right here, yeah, and or the engineering is the final. And you see, but everything in here is physics, right?
Yeah.
So now I want to go to initial major physics, and then I want everything to be initial major physics, which this is everything initial major physics. Like these both, when I do this, like across here is all initial major physics, and across here is all initial major physics. And then I only want to look at the engineers in here. So across this row, so this is the row percentage, 22.89. There were 19 people who had an initial major of physics who ended up being engineers. 19 divided by 83 is 22.89%.
So that answer should be
89. Yeah, and then double check because you see the other right here. If you use this doesn't make sense because does that look like 12% or 38%? That other right there.
12%.
That other. No, look at how you see you see that?
20, like 28.
Maybe close 38, right? It looks more than 12.
Yeah.
But you see that right here because you can check because it has to be more than 25. Does that make sense? Like this box right here. This box has to be more than 25. So 12 has to be wrong. So if you do here 32 divided by, so you can check 32 divided by 83, and then you see if it makes sense, and that's that number. So you say, okay, there were 32 people who had an initial major of physics and then went into other. So they had an initial major of physics and went into other. So and that makes sense right there. So just double check your numbers, see if it makes sense, and if it doesn't, it's it's a pick a number type thing. You're welcome.
With that same question, how did you know that the biology majors were less likely to switch to engineering? Do we just
This right here, this is, you see, these people were more likely to switch because the bigger this box is, the more of them are going into engineering. So, yeah.
And I had one other
Sure,
question.
sure.
I know like the stuff our potential of our clickers
Yeah.
that determines like
I'm talking about the amount